Hi to everyone, welcome to NC's channel. My name is Naresh, chemistry lecturer. Today I would like to discuss one of the topic from P block elements, and that is inert pair repeat. Inert pair repeat. This is the most important concept in mains, eamcet and neet. Now coming to inert pair repeat. This effect mainly you can observe third A group, fourth A group, and fifth A groups of P block elements. Now coming to third A group. Now we observe inert pair repeat in third A group elements. Now I have taken third group elements boron, aluminum, gallium, indium, thallium. Boron, aluminum, gallium, indium, thallium. Now coming to electron configuration. Boron electron configuration is helium 2s2p1. Aluminum electron configuration is neon 3s2 3p1. Gallium electron configuration is argon 3d10 4s2 4p1. Indium electron configuration is krypton 4d10 5s2 5p1. Thallium electron configuration is xenon 4f14 5d10 6s2 6p1. So these are the electron configurations. Now coming to valence electrons. So what is meant by valence electrons? Number of electrons present in valence cell or valence orbit are called valence electrons. Number of electrons present in valence cell or valence orbit are called valence electrons. So what is meant by valence cell or valence orbit? The last orbit present in atom is called valence orbit, or the last cell present in atom is called valence cell. Now coming to boron. In boron, second cell is the valence cell. It contains 2 plus 1 3 valence electrons. Coming to aluminum, third cell is the valence cell. It contains 2 plus 1 3 valence electrons. Now coming to gallium, fourth cell is the valence cell. It contains 2 plus 1 3 valence electrons. Now coming to indium, fifth cell is the valence cell. It contains 2 plus 1 3 valence electrons. Now coming to thallium, sixth cell is the valence cell. It contains 2 plus 1 3 valence electrons. Now every element in the group contains 3 valence electrons, 3 valency electrons. And you know that valence electrons only participate in bond formation. That's why every element in third group can form 3 bonds with 3 atoms like BCl3, AlCl3, GaCl3, like that. And also can exhibit plus 3 oxygen state. Every element can exhibit plus 3 oxygen state due to presence of 3 valence electrons. Now coming to thallium, the electron configuration of thallium is xenon 4f14 5d10 6s2 6p1. So this thallium contains f and d orbitals. Already you know that f and d orbitals are 4 sealing orbitals. That means these f and d orbitals cannot screen or cannot stop the nucleus force of attraction without falling on valence electrons. That's why nucleus force of attraction is more on valence electrons. Mainly the nucleus force of attraction is more on 6s orbital compared to p orbital, because s orbital has more penetration power towards nucleus. That's why nucleus force of attraction is more on s orbital compared to p orbital. So s orbital contains 2 electrons. These two electrons under the influence of thallium. That's why these two electrons have no interest to participate in bond formation, because nucleus force of attraction is more, and these two electrons under the influence of nucleus. That's why these two electrons have no interest to participate in bond formation. Only this electron has interest to participate in bond formation. That's why it can exhibit plus 1 oxidation state instead of plus 3. Here plus 1 oxidation state is more stable compared to plus 3 oxidation state. So this effect is called inert pair effect. So what is meant by inert pair effect? The reluctance of NS electrons to participate in bond formation is called inert pair effect. The reluctance means not willing, no interest to participate in bond formation. So that is called inert pair effect. The reluctance of NS electrons to participate in bond formation is called inert pair effect. Now coming to indium. So due to presence of d orbitals, it can also exhibit inert pair effect, but the effect is less compared to thallium. It can also exhibit plus 1 oxidation state along with plus 3 oxidation state. Now coming to gallium. So due to presence of d orbitals, it can also exhibit inert pair effect, but the effect is less compared to thallium. So that's why it can also exhibit plus 1 oxidation state along with plus 3. Now coming to aluminum and boron. So there is no d orbitals, there is no d electrons. That's why these aluminum and boron cannot show inert pair effect. That's why these cannot form plus 1 oxidation state. Now when we are moving from top to bottom, plus 3 oxygen state is decreasing and plus 1 oxygen state increasing. So we can observe that when we are moving from top to bottom, boron to thallium, plus 3 oxygen state is decreasing. Plus 3 oxygen state is decreasing. And plus 1 oxygen state is increasing. So this is the increasing order of plus 1 oxygen state. Now I will give one example. That is TlCl3 and TlCl. So which compound is more stable? So this is the most important example. In TlCl3 the oxygen state is plus 3, and in TlCl the oxygen state is plus 1. Now in thallium, which oxygen state is more stable? So plus 1 oxygen state is more stable. That's why TlCl is the most stable compound. Now give another example. InCl3 and InCl. So which compound is more stable? So in InCl3, indium oxygen state is plus 3. In InCl, the oxygen state of indium is plus 1. In these two, in indium, in the two oxygen states, which oxygen state is more stable? So plus 3 oxygen state is more stable. Because inert pair effect is less compared to thallium. So that's why the most stable compound is InCl3. Next example is GaCl3 and GaCl. So which compound is more stable? Here in GaCl3 the oxygen state of gallium is plus 3. In GaCl the oxygen state of gallium is plus 1. So which compound is more stable? So in gallium it can exhibit plus 3 and plus 1 oxygen state, but plus 3 oxygen state is more stable. That's why the compound GaCl3 is more stable. Only in thallium plus 1 oxygen state is more stable compared to plus 3. That's why TlCl3 and TlCl is the more stable compared to TlCl3. So in this way you can explain inert pair effect in third group elements. Now coming to fourth group elements. So fourth group elements, what are the fourth group elements? Carbon, silicon, germanium, tin, lead. Now coming to electron configuration. Carbon electron configuration, helium 2s2p2, silicon electron configuration, neon 3s2p2, germanium electron configuration is argon 3d10 4s2p2, tin electron configuration is krypton 4d10 5s2p2, lead electron configuration is xenon 4f14 5d10 6s2 6p2. So these are the electron configurations. Now coming to valence electrons. So number of electrons present in valence cell are called valence electrons. In carbon 2 plus 2 4 valence electrons present in carbon. In silicon 2 plus 2 4 valence electrons present in silicon. In germanium 2 plus 2 4 valence electrons present. In tin 2 plus 2 4 valence electrons present. In lead 2 plus 2 4 valence electrons present. And already we know that only valence electrons can participate in bond formation. That's why every element in fourth group element can form 4 bonds with 4 atoms, that is CH4, RCCl4, SiCl4, GeCl4, like that. Now so the oxygen state is plus 4. Every element can exhibit plus 4 oxygen state due to presence of 4 valence electrons. Now coming to lead. The electron configuration of lead is xenon 4f14 5d10 6s2 6p2. Now it contains F and d orbitals. Already you know that F and d orbitals are more shielding orbitals. That's why due to force shielding of F and d orbitals, these cannot screen or these cannot stop the nucleus force of attraction without falling on valence orbitals. The 6s2 6p2 are the valence orbitals. So F and d orbitals cannot screen or cannot stop the nucleus force of attraction without falling on valence electrons. That's why nucleus force of attraction is more on valence electrons. Mainly the nucleus force of attraction is more on s orbitals, because s orbital has more penetration power. That's why nucleus force of attraction is more on s orbital. So that's why these two electrons, s orbital contains 2 electrons. These 2 electrons under the influence of nucleus, that's why these 2 electrons no interest to participate in bond formation. only these two electrons has interest to participate in bond formation. That's why it can exhibit +2 oxidation state along with +4. So this +2 oxidation state is more stable compared to +4 oxidation state. Now coming to, so this effect is called inert pair effect. So what is meant by inert pair effect? The reluctance of S-electrons to participate in bond formation is called inert pair effect. So due to inert pair effect, this lead can exhibit only +2 oxidation state, is more stable oxidation state. Now coming to tin. So due to presence of d orbitals, it can also exhibit, tin also can exhibit inert pair effect, and that's why. But this effect is less compared to lead. That's why it also exhibit +2 oxidation state along with +4. Now coming to germanium. Now coming to germanium, due to presence of d orbitals, it can also exhibit inert pair effect, and this effect is less compared to lead. So it also can exhibit +2 oxidation state along with +4. Now in silicon and carbon, so there is no d electrons. That's why this silicon and carbon does not exhibit inert pair effect. Now when we are moving from top to bottom, +4 oxidation state is decreasing and +2 oxidation state is increasing. +4 oxidation state decreasing and +2 oxidation state is increasing. This is the most important. Now coming to, I will give one example, that is PbCl2 and PbCl4. Which compound is more stable? So in PbCl2 the oxidation state of lead is +2. In PbCl4 the oxidation state of lead is +4. So in lead, so which oxidation state is more stable? +2 and +4. So +2 oxidation state is more stable. That's why PbCl2 is the most stable compound. Now SnCl2 and SnCl4. SnCl2 and SnCl4. So SnCl2 and SnCl4, which compound is more stable? And GeCl2 and GeCl4. So which compound is more stable? Please comment me. In SnCl2 and SnCl4, which compound is more stable? In GeCl2 and GeCl4, which compound is more stable? Please comment me in comment box. Thanks to all for watching my video.